Welcome to The Explainer. Today, we are going deep. We're going to talk about 5G, but not the 5G you think you know, not just the little icon that pops up on your phone promising a slightly faster download. We're talking about the real, industrial strength, revolutionary 5G that's poised to change just about everything. And to really understand something this big, you can't just stick to theory and diagrams. You have to see it work. You have to get your hands dirty. That's why today we're doing a full deconstruction of a single powerful case study, Project Night Owl. This is a real-world, fully automated drone patrol system built from the ground up on a private 5G network. By tearing this project apart, piece by piece, looking at the hardware they chose, the software they wrote, and the incredible results they measured, we're going to uncover the real story. This isn't about hype. This is about revealing the future of automated networks, and it's happening right now.
So how are we going to tackle this? We're going to follow what I call an hourglass structure for this explainer. It's the best way to understand a complex topic like this. We'll start wide at the top, covering the big foundational concepts, the parts of 5G that are usually invisible to us, the stuff happening behind the scenes. This is the 5G you don't see. Then, the hourglass narrows. We're going to dive deep, focusing all our attention on one single point, the drone project itself. We'll go inside a real-world 5G lab and watch as the automated drone takes flight. This is where we get into the nitty-gritty details. And finally, once we understand that specific example with perfect clarity, we'll zoom back out. The hourglass widens again. We'll connect that one lab project to a massive global movement, showing how it fits into the bigger picture, from lab to global standard. And we'll look ahead to what this all means for the future of networks. It's a journey from the big picture to the forensic details and back out again. Let's get started.
All right, section 1. Let's talk about the 5G you don't see. You know, that 5G icon on your phone. Honestly, most of the time, it isn't telling you the full story. It's a bit of a marketing-friendly simplification. Because underneath the surface, there is a profound architectural revolution happening in telecom. And to truly grasp what's going on with our drone project, we need to understand the two absolute cornerstones of this revolution. The first is something called 5G Standalone, or SA, and the second is a movement called Open RAN. These two concepts are the engine driving everything else we're going to talk about today. They are the foundation.
Okay, please burn this slide into your brain. It is absolutely crucial. For the last several years, almost all the 5G you've ever used has been what's on the left, 5G Non-Standalone, or NSA. The analogy here is perfect. It's like adding a new, faster lane to the same old highway. Your phone connects to a new 5G radio, sure, so you get better speeds, but that radio is still plugging into the old 4G network brain, the Evolved Packet Core, or EPC. All the traffic control, all the logic is still running on a system designed a decade ago. It's faster, but it's not smarter. Now look at the right side. This is the revolution, 5G Standalone, or SA. This isn't just a new lane, it's a completely new highway system. It uses not only a 5G radio, but also a true brand new 5G core, the 5GC. This is the new brain. And this new brain unlocks entirely new capabilities that were literally impossible on the old 4G core. Things like network slicing, the ability to carve out a dedicated, guaranteed piece of the network for a specific task. Or, and this is key for our drone, the ability to process data locally. With SA, you can place a part of the network core, the user plane function, or UPF, right on site at the edge. This means a signal from our drone doesn't have to travel hundreds of miles to a central data center and back. It can be processed right there on campus. This is what gives you that ultra-low, almost instantaneous latency. It's an absolute game changer. SA isn't just about speed, it's about response time. So, if 5G Standalone is the new, smarter brain, our second key concept, Open RAN, is about changing who gets to build the body. For decades, mobile networks have been closed proprietary systems. If a carrier like AT&T or Vodafone bought a base station from, say, Ericsson, they had to buy Ericsson's software, Ericsson's radios, the whole shebang. You were locked into one vendor. This is called a monolithic system. Open RAN blows that entire model wide open. It's a massive industry movement to break up that single closed box into standardized, open, and interoperable components. Think of it like building a PC. You can buy a CPU from Intel or AMD, a graphics card from NVIDIA, and a motherboard from Asus, and you know they'll all work together because they follow common standards. Open RAN does the same for telecom networks. An operator can now buy a radio unit from one company, a distributed unit from another, and run software from a third, all on generic, off-the-shelf servers. This breaks the vendor lock-in, injects a ton of competition into the market, and ultimately sparks way more innovation.
So this slide shows you visually what that disaggregation from Open RAN actually looks like. Let's start at step 1. This is the old way, the traditional RAN. You had a radio head up on the tower, and it was connected by fiber to a big proprietary box at the base called a baseband unit, or BBU. That BBU was a black box, everything was inside it, and it all came from one vendor.
Now look at step 2, the split. This is the first big move in Open RAN. We take that monolithic BBU and we split its functions into 2 separate logical pieces. First, there's the distributed unit, or DU. The DU handles the really time-sensitive real-time radio functions, so it needs to stay physically close to the radio. Then there's the centralized unit, or CU. It handles the less time-sensitive, higher-level processing. Because it's less time-critical, you can centralize the CUs from many different cell sites into one location, which is more efficient. And that brings us to step 3, the cloud. This is the ultimate goal. Once you've split the CU and DU, you can turn them into software. They become virtualized. And instead of needing special proprietary hardware, they can just run as applications on standard commodity computer servers. This is what OCloud means. And you manage this whole virtualized system with another piece of software called an SMO, a service management and orchestration platform. This shift from closed hardware to open, virtualized software is the very heart of the modern, flexible network.
So, why do we go through all this trouble? Why build a standalone core? Why break everything apart with Open RAN? Because this new architecture unlocks the 3 true promises or pillars of 5G. The first one, eMBB, or Enhanced Mobile Broadband, is the one we all know. It's just faster. Faster downloads, smoother 4K streaming on your phone. It's great, but it's really just an evolution of 4G. The second one is MMTC, or Massive Machine Type Communications. This is totally different. This is about connecting billions of tiny, low-power, low-data devices. Think of smart water meters, soil sensors on a farm, or asset trackers in a shipping container. They don't need much speed, but they need to run on a single battery for years. But our focus today, the reason we're dissecting this drone project, is the third pillar, URLC. That stands for Ultra-Reliable Low-Latency Communication. This is the real game changer. This is for applications where failure is not an option, and a delay of even a few milliseconds could be catastrophic. We're talking about autonomous cars communicating with each other to avoid a crash, a surgeon in New York controlling a robotic arm in Tokyo, and, as we're about to see, an automated drone that needs instantaneous, absolutely fail-safe commands to track a target. This is the promise that only a true 5G SA network can deliver.
Okay, so we've laid all that groundwork. We understand 5G SA, Open RAN, and URLC. Now our hourglass is going to narrow. We're moving from theory to reality. It's time to get our hands dirty and go inside a real-world 5G lab at National Sun Yat-sen University in Taiwan. This is where a team of brilliant engineers and students took government funding and, instead of just running simulations, decided to build their own fully operational private 5G standalone network from scratch, using all of the Open RAN principles we just talked about. This is where the rubber meets the road.
And this quote from one of the project leads just captures the entire spirit of this endeavor perfectly. They could have gone to a big telecom provider and just paid a monthly fee for a private 5G service. It would have been easier. But they made a conscious choice. They said, no, we're going to spend this money on buying the actual hardware, the radios, the servers, the antennas, and we're going to build it ourselves. This engineering-first, hands-on philosophy is so important because when you build it yourself, you don't just use the technology, you understand it. You know its limits, you know its strengths, and you know how to push it to do things that nobody has ever done before. This decision was fundamental to their success.
Now look at this. This table is the beating heart of their machine. Let's break this down line by line, because every choice here is deliberate and meaningful. First, architecture. 5G SA with Open RAN. Right away, they committed to the real deal. No non-standard shortcuts. They wanted the full suite of 5G capabilities, especially the low latency, not just a speed boost. Core network. They used a Mavenir 5G core. Mavenir is a major player in the Open RAN space, providing the software-based brain for the network. This was a critical software component. Frequency band, N79, from 4.4 to 5.0 gigahertz. This is huge. This is a dedicated band specifically set aside in many parts of the world for private 5G networks. By using this, they guaranteed they wouldn't have to deal with interference from public cell phones, ensuring a clean, reliable signal for their mission-critical drone. Antenna, an 8x8 MIMO radio unit with 100 watts of power. Whoa! So what does that mean? MIMO stands for Multiple Input, Multiple Output. 8x8 means this antenna has 8 transmitters and 8 receivers. This allows it to send and receive multiple streams of data simultaneously, dramatically increasing capacity and improving coverage. And 100 watts is serious power. This wasn't a toy. Timing sync, a GNSS receiver. This might be the most underappreciated but most critical component on this list. Modern 5G networks, especially those that use time division duplexing, require hyper-precise, nanosecond-level timing synchronization across all components. Without a perfect, stable clock signal from a GPS or other global navigation satellite system, the whole network would just collapse into chaos. It's an absolute must-have. And finally, infrastructure, a 9-meter pole with dual fiber rings. This tells you they built this to last. They put the antenna up high for good coverage, and the dual fiber rings mean they had a redundant, fault-tolerant connection back to their core network. If one fiber line got cut, the other would keep everything running. This was a professional-grade deployment through and through.
Before we get to the drone, the team used their powerful new network for another demanding application, coastal security. They faced a common problem. A security camera would spot a person of interest, but from a high angle where you couldn't see their face. So how do you track them when they move into the view of another camera? Their solution was brilliant. They used the massive bandwidth of their 5G network to stream high-definition video to an AI model that could analyze a person's unique walking style, their gait. As you can see from the chart, the results were stunning. Before, trying to match the person across cameras based on appearance alone gave them a paltry 36.5% accuracy. But by adding in the AI-powered gait analysis, which was only possible because of the 5G network's high bandwidth and low latency, their accuracy skyrocketed to over 80%. It's a perfect example of how 5G acts as an enabler for real-time AI. But even this wasn't the ultimate test.
And now we arrive at the main event, the ultimate test of their network, specifically its ultra-reliable low-latency communication, or URLC capabilities. Their grand challenge was to create a fully autonomous drone security patrol system, a system where a human doesn't fly the drone with a joystick, but where the network and the software do everything automatically. Let's break down exactly how this mission works, step by step. The entire mission is a seamless, 4-step automated sequence, orchestrated entirely by software communicating over their private 5G network. It starts with step 1, detect. A stationary ground camera, which has a wide field of view, is constantly watching. It uses a well-known AI object detection model called YOLO4 to identify anything that shouldn't be there, an unauthorized person or a boat getting too close to shore. The instant it gets a positive ID, the system triggers step 2, fly. The system's central computer immediately generates a flight command using a protocol called Mavlink. This command, which includes the intruder's last known GPS coordinates, is blasted over the 5G network to the drone, which is waiting in its hangar. The drone's motors spin up and it launches, flying autonomously to those coordinates. Once it arrives overhead, we hit step 3, track. The drone's own onboard camera takes over. It locks onto the target and begins to actively follow it, all while streaming high-definition video back to the control center over the 5G link for evidence. Finally, once the target leaves the area or the mission is otherwise complete, the system initiates step 4, return. The drone automatically disengages, flies back to its home base, and executes an automated landing sequence. No human intervention required at any stage. It's a complete machine-to-machine loop. The technology stack they use to pull this off really showcases their ingenuity and resourcefulness. For the drone itself, they used both 6-axis and 4-axis models, depending on the payload requirements. But here's the cool part. The brain on board the drone was a simple, inexpensive Raspberry Pi. This is off-the-shelf hardware, accessible to anyone. For flight control, they used the standard Mavlink protocol, but, and this is clever, they created custom payload extensions. This means they actually modified the protocol to embed their own specific commands and data right into the flight control stream. Communications, of course, was the key. They used a standard 5G dongle, the kind you could buy online, but they paired it with their own custom SIM card. That SIM was the golden ticket that gave the drone access to their private, high-performance 5G SA network. For AI, as we mentioned, they used YOLO V4 for object detection, and for positioning, they started with standard GNSS for general flight, but later, to nail those tricky autonomous landings, they added a dedicated ground-based RTK station to get centimeter-level precision. Every piece was chosen for a reason.
So to prove their network was actually better, they couldn't just say it feels faster. They needed hard numbers. So they devised 2 brilliant custom key performance metrics, or KPIs. The first they called CTT, which stands for capture to trigger. This measures the entire system's end-to-end reaction time. It's the total time elapsed from the very instant the ground camera sensor captures an image of an intruder through the AI detection, the command being sent over the network, to the moment the drone's motors physically start to spin up. It's the measurement of total system responsiveness. The second metric is ITM, or instruction to move. This one is more focused. It isolates just the agility of the network control link. It measures the time from the moment the control center issues a new command, like move left, to the moment the drone's propellers physically change their pitch and the drone begins to move. Essentially, CTT measures the whole system's reaction time, while ITM zeroes in on the pure control link latency.
And here is the data climax. This is the payoff. The team tested the entire system twice, once running over a standard commercial 4G network and once running over their own private 5G standalone network. The results, measured in milliseconds, are absolutely dramatic. Let's look at the system response time, CTT. On 4G, it took 249 milliseconds. On their 5G SA network, it was just 153 milliseconds. That is a 40% reduction. The entire system just reacted almost twice as fast. But now look at the control latency, the ITM. On 4G, it was a sluggish 757 milliseconds, nearly 3/4 of a second of lag between sending a command and the drone moving. That's an eternity when you're trying to track a moving target. On their 5G SA network, just 301 milliseconds. That is a staggering 60% improvement. The drone's responsiveness on 5G was more than double what it was on 4G. And why? Why this massive difference? It comes directly back to that 5G standalone architecture we talked about. With the local UPF on campus, the control signals never had to leave the university to travel across the public internet and back. They stayed within a tight, local, super fast communication loop. This isn't a theoretical advantage. This is the measured, real-world superpower of true 5G in action.
Okay, it's time to start zooming our hourglass back out. What we just saw was an incredible achievement for a single university lab. But it's crucial to understand that this project wasn't happening in a vacuum. The concepts they proved, the power of standalone 5G, the flexibility of Open RAN, and the potential of automation, are not niche academic ideas. They are at the very center of a massive global shift that is happening across the entire telecom industry right now. Let's connect the dots. This timeline gives you a sense of the global context. We're in a pivotal year. At the end of 2024, the official standards body, 3GPP, finalized Release 18. This is also known as 5G Advanced, and it formally standardizes many of the capabilities needed for these advanced automated systems. Then, throughout 2025, you see the ecosystem kicking into high gear. The O-RAN Alliance, the group pushing for open networks, is holding its regular plug fests. These are massive events where hundreds of engineers from different companies all bring their gear and literally plug it all together to test interoperability and iron out the kinks. At the same time, you have crucial open-source projects like Nefio, backed by Google and the Linux Foundation, hitting major release milestones. Nefio is all about bringing cloud-native, Kubernetes-based automation to the telecom world. All of these parallel efforts, standards, hardware interoperability, and software automation are converging, creating a perfect storm of innovation.
And if you need proof that this isn't just talk, look at where the global telecom giants are putting their money. This is happening now, at massive scale. In the UK, Vodafone is in the middle of a project to replace 2,500 of its existing mobile sites with new Open RAN-based solutions. They're also using AI to make those networks more efficient. In Germany, Telefonica has deployed a commercial cloud RAN. That means the public network that people are using every day is now running on virtualized software in the cloud. And in the US, AT&T signed a huge, multi-year, multi-billion-dollar deal with Nokia specifically to use AI and automation to improve how their network operates and to save energy. Meanwhile, you have new industry groups like the AI RAN Alliance, which has already grown to over 100 member companies, all pushing to design future networks to be AI native from the ground up. The principles proven in that little drone lab are now central to the multi-billion-dollar strategies of the world's biggest operators.
The term network automation can feel really abstract and vague, so I want to show you what it actually looks like in practice. This right here is what we call infrastructure as code. This is a configuration file from that Nefio project we mentioned. Now, don't worry about the syntax, just look at the plain English words. An operator doesn't have to manually log into 100 different devices and type in thousands of cryptic commands anymore. Instead, they just declare what they want. They declare their intent. Look at the kind line. It says RAN slice intent. The operator is stating their intention to create a slice of the radio access network. They give it a human-readable name, Campus UAV Patrol. And then comes the magic, under policies. They simply state latency budget MS 20. They are telling the network, for this drone patrol slice, I need a connection with 20 milliseconds of latency or less, period. They declare the what, not the how. The automation platform reads this simple text file and then does all the incredibly complex work in the background, configuring the radios, the core, the transport, to make that 20 millisecond promise a reality. This is how you manage a complex, modern network at scale.
And so we arrive at our final section. We're going to bring it all home. We'll synthesize everything we've learned, bust a couple of very common myths about 5G, and look at the bigger impact of this massive shift towards the automated radio access network, both in terms of business and for the people who build and run these networks.
Before we wrap up, let's use what we've learned to bust two of the most common myths you hear about 5G and Open RAN. First, the myth that higher frequency equals faster speeds. This is not strictly true.
The thing that's actually key for data rates for speed is wider bandwidth. Think of it like a highway. It's the number of lanes that determines how many cars can get through, not the speed limit. The only reason higher frequencies are associated with higher speeds is because those high-frequency bands, like millimeter wave, just happen to have much wider unused swaths of spectrum available. The trade-off is that those high-frequency signals are very fragile and don't travel far, which is why you need advanced technologies like massive MIMO to make them practical. The second myth is that Open RAN is automatically cheaper. This is a very important and nuanced point. While the cost of the individual hardware components, the capital expenditure or CapEx, might be lower because of increased competition, the cost of running the network, the operational expenditure or OpEx, can actually go up. Why? Because now you have to integrate and manage equipment from multiple different vendors, which is incredibly complex. The only way the math works, the only way the total cost of ownership, TCO, actually goes down is if you pair Open RAN with robust, powerful automation platforms like an SMO and a RIC to handle all that complexity for you. Automation isn't just a feature, it's the key that unlocks the economic promise of Open RAN.
Now, this whole transformation is not without its hurdles. It's not a simple path. But the key takeaway is that for every single challenge, there is a massive, industry-wide effort to create an opportunity. Yes, the challenge of multi-vendor integration is very real and very complex. But the opportunity is that industry-wide plug fests and new certification programs are maturing every day to solve exactly this problem. Yes, opening up the network introduces new potential security risks, but the opportunity is that the industry is moving away from old castle and moat security and standardizing on a much more robust zero-trust security model fit for this new environment. And yes, there is a huge challenge right now in the form of a skills gap. The engineers who grew up configuring hardware boxes need to learn new skills in cloud-native software, in AI, and in automation. But the opportunity is immense. New, exciting roles are being created, and open-source projects like Nefio are not only building the technology, but also defining the career path for the network engineer of the future. The road ahead is challenging, but the path is becoming clearer every day.
We've seen it all. From the foundational architecture of 5G standalone, to the nuts and bolts of a drone project, to the global movement towards automation, it all points to a future where the network largely runs itself, a network that can predict its own faults, heal its own failures, and optimize its own performance, all automatically, with AI in the driver's seat. And this leaves us with one final profound question to think about. When the network runs itself, what is our role? What is the role of the human engineer? Perhaps we stop being mechanics, constantly in the weeds, fixing problems. Perhaps we become architects. We shift our focus from managing complexity to directing intelligence. We're the ones who write that intent file. We're the ones who tell the network what to do, and we let the automation figure out how to do it. That is the future that Project Night Owl reveals, and that is the true, ultimate promise of the automated RAN. Thanks for joining us on The Explainer.